Okay, so let's start. Good evening, everybody. So today is the third problem solving session of second. Yeah, let's start today's lecture. So everybody is able to see the presentation, right?
Yes, ma'am.
Okay. So in last week we talked about bipolar junction transistor and its static characteristics, dynamic characteristics, all these things. We also saw the different power losses that occur in a BJT, and along with that we solved some problems related to BJT, right? So today we will start MOSFET and IGBT. These two devices are very important in terms of power electronics because nowadays MOSFET and BJT, these two devices are really important for designing converters for the different applications. Both of these switches are controlled switches, and we shall see the different characteristics of these devices today. So the left hand side, this symbol is the symbol of a MOSFET, right? So as you can see, there are three terminals here because this is a control switch. So here, this terminal, we call it drain terminal. This terminal here, we call it source terminal. And this terminal here, we call it as gate terminal. Okay. So uh, I shall write it here. So this one is drain. The bottom one is source, this one. And there is a third terminal, which we call the gate terminal, right? So these are the three terminals. So how is it different from a BJT? Last week we talked about BJT. So this was also a control switch. So you may ask that what is the how MOSFET is more advantageous, or why MOSFET is why should we use MOSFET? Because we already have BJT, which is a controlled switch, and it can block voltage in the forward direction, and it can carry current from collector to emitter for a NPN transistor. So why do we need MOSFET? So there are some differences of MOSFET from BJT. MOSFET is a bit different from BJT. How is it different? First of all, if you see, for BJT, this third terminal, this control terminal, which we called as base, This terminal is not insulated from collector or emitter terminal. Base terminal is directly connected electrically with collector terminal and emitter terminal. But for MOSFET, if you look at the symbol, here there is a gap between the gate terminal and the drain and source terminal, right? There is this gap. This gap symbolizes that the gate terminal is electrically insulated from the drain and source terminals. So this terminal is not electrically connected to either source or drain. So first difference is this one. So the control terminal is electrically insulated from these two terminals. That's why the full form of MOSFET, if you know, the full form of MOSFET is metal oxide semiconductor field effect transistor, right? So this there is a insulating layer between the gate terminal and this substrate, this terminal. Okay, this is the first difference. And what is the second difference? The second difference is if you see the characteristics, IV characteristics for BJT, BJT can block the voltage in forward direction and it can carry forward current. Forward current means for a NPN transistor, it can carry current from collector towards emitter in this direction, right? From here to here. But here you can see for in the IV characteristics that the current is bidirectional. So basically MOSFET can carry current from drain to source as well as from source to drain. How this carries current in both the directions that we will see in later slides. But for now you just remember that MOSFET can carry in both the directions. So this is a huge advantage, right? In some applications we require bidirectional current capability. So for those applications, MOSFET is more advantageous than BJT. Okay. So if you see the physical structure of a MOSFET, this is the symbol, obviously, drain, source, and gate. And if you see physically, so as I said earlier, that there is this insulating layer, and over this insulating layer, there is a there is metallic part from which we can access the gate terminal. So from here, there is a metal deposition over the insulating layer. And here there is a NPN tag like this, right? So how MOSFET turns on, like what happens when the MOSFET is on and what happens when the MOSFET is off and how the MOSFET is turned on. So another difference like from BJT is that for BJT we saw that BJT is a current control device. Whenever we provide base current, BJT starts to conduct. BJT becomes on, right? We need to provide some base current. But for MOSFET, MOSFET is a voltage control device. Why? Because if we provide a positive gate to source voltage, then only the MOSFET will be able to conduct or the MOSFET will go to on state. With like the gate to source voltage, we have to provide a positive voltage. The gate will have to be positive with respect to the source. So there is no question of current. If you provide a gate to source positive gate to source voltage, then the MOSFET will conduct. There is another parameter which we call it the as the threshold voltage, gate to source threshold voltage. So the positive voltage that we apply here, that must be greater than the threshold voltage. If we apply a voltage that is greater than this threshold voltage, then only the MOSFET will be on. What is the threshold voltage that we will see later, but the positive voltage has to be greater than the threshold voltage for the MOSFET to turn on. So based on this voltage, we can dictate whether the MOSFET is on or off. So this is not a current control device. This is essentially a voltage control device, right? So if you provide a positive gate to source voltage like this, suppose you have a voltage source here that is providing the gate to source voltage, and here you have a DC voltage, right? So the moment you provide a gate to source voltage here, which is greater than the threshold voltage, because there is a insulating layer, so there is definitely some capacitance, right? Because here there is a metallic part which can be the positive terminal, and in between there is some insulator, and here you have a NPN channel. So there has to be some channel for the MOSFET to carry current. So here there is N-type material, here there is P-type material, again N-type material. So some channel, some sort of channel has to be formed for the MOSFET to conduct current. So the moment you apply positive voltage here, due to the capacitive action, um, the electrons will start getting attracted towards this, like this will act as the positive plate of the capacitor, and this side will act the negative plate of the capacitor, and the electrons will get attracted towards this portion. And as the electrons are stored here, so the channel is formed from N toward there are these electrons, and again there is N-type material. So now the current can flow from drain to source as well as source to drain through this channel, as there are electrons here. The moment you withdraw this voltage, then again the electrons will disperse and the channel will the channel will be closed. There will be no channel at all. So again it will like its impedance will be very high and it will be off. It will no longer carry current. So this is the mechanism of MOSFET, the operating principle, right? And this channel that is formed here, we call it as the inversion layer. Okay. So this is basically a NPN a enhancement type MOSFET. There are some other kinds of MOSFET that you can refer to, and you can see the lecture, Umanand sir's lecture. There he has explained different kinds of MOSFET, which are enhancement type MOSFET and depletion type MOSFET, right? So you can see in the lecture. Now, yeah. So, so here what I have shown is the static characteristic of a MOSFET. So in the last class, we saw the static characteristic of a BJT, where in the x-axis we had the collector emitter voltage VCE, and in the y-axis we had the collector current IC. The static characteristic was IC versus VC. Similarly, for MOSFET also, we shall see the static characteristic where in x-axis we have the drain to source voltage VDS, and in the y-axis we have the drain to source current IDS. Okay. So this picture actually I have taken from the datasheet of a SiC MOSFET, silicon carbide MOSFET. So I have written the I have provided the link here. You can check afterwards. It is a SiC MOSFET from Wolfspeed. Okay. So this is a 1.2 kV 32 milliohm SiC MOSFET. You can also see like some silicon MOSFET. This is a silicon carbide MOSFET. These MOSFETs are called wide bandgap devices because here you will see that these MOSFETs are very efficient and they are very fast. They are faster compared to the silicon MOSFET and other, yeah, from silicon MOSFET. So you can check other different types of data sheets. Here I have provided the SiC MOSFET data sheet that I have sorry, the static characteristic of the SiC MOSFET. So these portions are basically the you can draw an analogy from the BJT. These portions are kind of the linear portions, right? Where you will see like afterwards it kind of becomes if you remember the last class, afterwards it becomes kind of constant, parallel to the x-axis. But in this portion, the characteristics are almost linear. So from these curves, we can get the RDS on. If you just get the slope here, the slope will be nothing but RDS on, right? So yeah, here in the y-axis we have the drain current, and in the x-axis we have VDS. So the slope will be delta y by delta x will be current by voltage. So if you just get the reciprocal of that, you will get the RDS on, the resistance of the MOSFET during turn on condition. And like BJT, in BJT we had the control parameter which was the base current. Here the control parameter is the gate to source voltage. So for different gate to source voltage we have the characteristics for 7 volt, 9 volt, 11 volt, 13 volt and 15 volt. Right. So this is the static characteristics. Uh, Right. And here we have some conditions like what is the junction temperature? The junction temperature is 25 degrees Celsius. So if you actually see the data sheet, you will find these static characteristics for different junction temperatures at 25 degree, at suppose 100 degree or 125 degree or 150 degree. So for various temperatures, you will get these characteristics, right? So far, okay. Does anybody have any question?
Excuse me, ma'am.
Yeah.
Madam, how static characteristics differs from dynamic?
So basically, a static characteristic is that you will have in the x-axis and y-axis, you will find like some voltage or current parameter. For example, in this here, we are seeing in the x-axis we have the drain to source voltage, and in the y-axis we have the drain current, right? So for static characteristics in x and y axis, you will have some current or some voltage. But if we see the dynamic characteristics, there you will see the current and voltage waveforms with respect to time. How the voltage and current waveforms vary in on condition, in off condition with respect to time. So that is called a dynamic condition. Okay.
Okay, madam. Thank you.
Yeah, so if you take any device, so you will get some static characteristics, and these characteristics are given in the data sheet. You will also see a dynamic characteristics. I think I showed you in last problem solving session also. So dynamic characteristics is your voltage versus time, then current versus time, control signal versus time. All these things are called dynamic characteristics. I will show for MOSFET also. But before that, we shall see some other characteristics. Okay. Yeah. So this graph is basically the drain to source current versus the gate to source voltage. This is also called a transconductance characteristics. Why? Because here in the x-axis we have the control voltage, that is gate to source voltage, and in the y-axis we have the current, right? And here also they have given the curves for three different temperatures: 25 degree, minus 40 degree. This one, the mid one is 25, and this one is for at 175 degree, right? So, so if you want to get a relation between the drain current and the gate to source voltage, that is given by this equation. So ID is basically a constant K times VGS minus VGS threshold square. So earlier I told you that unless we give a particular positive voltage, gate to source voltage, the MOSFET will not turn on. That voltage is called gate to source threshold voltage. If you don't cross this threshold voltage, the MOSFET will not turn on. So from this formula, you can get the relation between ID and VGS. And for finding out K, just you can just refer to this formula. So all this, so for a particular operating point, this IDS on, then VGS and VGS threshold, all these parameters will be given in the data sheet. So from there you can calculate K, right? So yeah, so this is the transconductance curve for the MOSFET. Yeah. While talking about the difference between MOSFET and BJT, I told you that MOSFET can carry current in both the directions, right? So how does it carry current in both the directions? Because if this is the structure of a MOSFET, so here again there is this insulating layer and this is gate terminal and there is this NPN stack. So internally, this P and this source and this P, they are connected internally. Like here I have shown this line, but in the package only, in the MOSFET package only, this this P type material, this P layer and the source, they are connected, right? So what happens then? What it signifies is that, like if you see this portion here, we have a PN junction, right? So from source towards drain, we will have a diode because there is a PN junction present and this P is connected to the source. That's why from source to drain, there will be a diode. So even though you have withdrawn the pulse from the MOSFET channel is not formed, then also current can flow from source to drain via this PN junction. So because for diode there is no control signal. If the diode is forward biased, then the diode will start conducting. So if you get a positive voltage at source terminal, basically if the source is positive with respect to the drain, then this junction gets forward biased and current can flow from source to drain. Right? So when for some voltage source converters, if you have some inductive load, so, if some inductive load is present, then sometimes it needs a freewheeling path, right? During the dead time. So, during that time, it needs a current path because you can't interrupt inductor current all of a sudden. Then there will be a huge di by dt, and that will cause the devices uh, to get bad, right? So, to provide a path for the inductive load for the inductor, there is a requirement that the devices have to be bidirectional, right? Bidirectional in terms of current flow capability. It needs to carry current in both the directions. So for those purposes, MOSFET is good. MOSFET is advantageous. Okay. So till this point, everybody is okay with all this. Everybody is okay. Okay. So we will go to the next slide. Yeah, so one of you were asking about the dynamic characteristic. This is the dynamic characteristic. Here in the x-axis we have time and in the y-axis we have VDS and ID. This is the dynamic characteristic of the MOSFET. So this is very similar to BJT, like similar in the sense that for BJT also we saw similar characteristics, right? The on to turn off and turn off to turn on transitions. So here also we can see that here the MOSFET is blocking voltage. So the voltage has a high value and the current is almost zero. Right. There is a very small amount of leakage current but that current is very small. So you can kind of neglect it. So in this portion, the MOSFET is off. Now you are providing the, like you have started providing the gate signal. So what will happen? This is called the turn on delay time. Here, what happens is the gate voltage starts rising, but it is still within V threshold. So it has not crossed V threshold. That's why the current is still zero. Unless V threshold is crossed, current will not start rising. So here, although you have provided some gate voltage, but it is not sufficient. That's why the current is still zero and it is still blocking the voltage. After that, the moment the gate voltage crosses the V threshold voltage, then the current starts rising. The current starts rising, and then after during the rise time, it starts and reaches the total current, like the load current, and the voltage drops here, because as the current starts rising, the voltage has to drop, and it drops to almost like zero, very small voltage. And in this period, this is the on period of the MOSFET, where it conducts the current. So here, whatever VDS you get, that is ID times RDS on. So there the MOSFET channel has some resistance, which is very small. So that resistance times the current, whatever is the voltage, that is VDS drop during on condition. Right. Then again, when you withdraw the gate pulse, so now you need to go from on condition to off condition. So now you withdrew the gate pulse, but this is called the off delay time. During this portion, the current is still maintaining and the voltage is still there, the voltage drop is still there, very small amount of voltage. And after this delay time, the current starts falling and the voltage starts rising, and again it goes to the total blocking voltage, that it like the total voltage, and the current becomes zero. This is a full cycle of the MOSFET, right? So P total is conduction. So some whenever there is overlap between voltage and current, there will be loss. Here there is the turn on loss, because current is also here present and voltage is also present. So turn on loss, here turn off loss, and here conduction loss. So the summation of all these losses provides us the total loss of the uh, MOSFET. Okay. So, and this is a picture of a heat sink. This is also industry available heatsink. It's this is called the part number. This code CR201755AE. You can search it afterwards. So there are different kinds of heat sinks. This is one of them. So you can see these clips, right? So I just wanted to show like how physically, like how you just can connect the devices with the heat sink practically. So you can see the legs. So these are the actual devices, and they are connected to the heatsink surface via these clips. And while connecting the device, there will be some uh, thermal interface material that should be in between the device case and the heatsink surface. Okay. So that's how we connect the devices with the heatsink. There are different other heatsinks where there you wouldn't see this clip arrangement. There will be some other arrangement for connecting the devices. Okay. So yeah. Uh, Here is the thermal circuit that was also discussed earlier. So how will you select the heatsink, right? So if you see, there will be some loss that we already discussed. There will be some loss in the MOSFET, and this is suppose this node is suppose the device junction, and here you have a thermal resistance which is theta r theta Jc, which is junction to case thermal resistance. There is another resistance which is case to sink, when case to heat sink basically. Then you have this node where this is the heat sink temperature. Then again you have another r theta which is sink to ambient. So there are these three resistances. If you have calculated the loss, the total power loss, then and you already know, like suppose you want to restrict the junction temperature at 120 degree, okay? So, and you also know the ambient temperature. So, if these three quantities are known, you can calculate R theta J junction to ambient. Junction to ambient means the temperature difference, the total resistance, like from this point to this point, what is the total resistance in this whole region. As you have the value of R theta junction to ambient, and this we already know that this junction to ambient resistance, this is basically the summation of these three resistances: junction to case to heatsink, and heatsink to ambient. Junction to case R theta you can get from the datasheet of the device. Case to heatsink temperature also you can get, like whatever interface material you are using to connect the device with the heatsink, that will have some resistance, so that you can get from that also, you can, like that data you will have. And so you need basically sink to ambient temperature. What will be this? The rearranging the equation, we can have this equation. So you know this one from this formula. You know junction to case R from the data sheet, and you also know this. So you can calculate the sink to ambient temperature. So if you see that, then after calculating this, you will choose some heat sink, and that heat sink will have some sink to ambient temperature, and that should always be lower or equal to this value, not more than this. Otherwise the junction temperature will be more than what you have designed it for. If you want it to be 120 degree, it will not be 120 degree, it will be more than that if this R theta is more than your design value, okay? So whatever heat sink you will choose, the theta of that heat sink, like so the thermal resistance of the heat sink should always be lower than this calculated R sink to ambient, okay? So that's how you can select the heat sink for your device. Next we have the IGBT, insulated gate bipolar transistor. IGBT is another control device. So for IGBT also you will get three terminals. The top one is collector, the bottom one is emitter, and this one is gate. Okay. So here also the gate is insulated from this power terminals, and here you have a PN this kind of stack. And if you kind of divide it here, like if you just get a line, so here you can see there is a PN junction. So this PN junction we can represent as a diode, and then you have an NPN, right? NPN stack, which is kind of similar to a MOSFET. So you can represent a IGBT like this, a diode in series with a MOSFET. But here you will have to what you will see, that this device can't conduct current in the reverse direction. It can only conduct current from this to this, because there is this diode. That's why it will not allow current in the reverse direction. IGBT can conduct current only from collector to emitter. Okay. And this is the static characteristics of the IGBT. So here you have V collector, and here you have the current, collector current, and this is more or less similar to BJT and MOSFET. So here there is this linear region. Afterwards, it kind of becomes flat. And BJT can also block voltage in the reverse direction, right? It can obviously block voltage in the forward direction, but in the reverse direction also it can block voltage, but up to a certain limit. Afterwards, it breaks down. So the characteristics of BJT is voltage, it can block voltage in either direction and forward current. So this portion is the operating region of IGBT. Another kind of device is called ACR. So ACR, there is a ACR family. There are different types of devices. So the most common one is silicon controlled rectifier. Okay. So ACR, earlier ACR was a very popular device, but nowadays MOSFETs and IGBTs are more prevalent. But earlier, if you see all the converters, in all the converters, ACR was used. Okay, so the symbol of ACR is something like this, similar to a diode, but there is one control terminal. There is a third terminal. And ACR can block voltage in both the directions. Unlike diode, diode could only block voltage in the reverse direction, but ACR can block voltage in both the directions. But it can carry current only in one direction, from from anode to cathode, just like diode. But the difference is it can block voltage in the forward direction as well, because we have this control terminal. So for ACR, the turn on is controlled. You can control, like you can dictate when you want it to on, but the turn off is uncontrolled. So that's why it is also called a semi-controlled device, because the turn on phenomena is a controlled phenomena, but the turn off phenomena is uncontrolled. You can't dictate when it will get turned off. And this is the static characteristic of the ACR. So this voltage is called the forward breakover voltage. And if you don't provide any signal, like gate signal here, it will go till this point, and then there is this negative resistance region. Afterwards it will start conducting, and if you provide gate signal, then the curve will, like there will be a family of curves. See, like the more the gate current, so Ig1 is the highest, so the characteristics will be like this. If for Ig2 it will be like this, for Ig3 it will be more, and then like this. So based on the gate current, the characteristics will change here, and then the current will rise like this. And in this region it will block voltage. There will be some leakage current, as we also saw for diode, and at the reverse breaking voltage it will break down. So the blocking voltage should be within this region. Okay, it should be lesser than the breakdown voltage. This is SCR. So before we go to the problem solving part, does anybody have any question? Uh, did you ask anything? Actually, I couldn't get. Uh, okay, so if you don't have any question before going to the problem solving part, we shall take a 5 minute break. So now it is 6:48. We shall join at 6:53. Okay. Yeah. Uh, let's start the problem solving part. The slide is visible to everyone.
Yes, ma'am.
Okay. Uh, the first problem is consider the circuit in the figure which consists of an ideal MOSFET and an ideal diode. The gate to source voltage applied to the MOSFET is illustrated in the figure. Find the average voltage across A and B. So there is this voltage source, and then there is this diode, a resistance, and here there is a MOSFET, ideal MOSFET, they have told. And you are giving some gate pulse here, and the gate pulse, the profile of the gate signal is given here. So the duty is 0.6 here, because for 60% of the time period the pulse is given, and for rest of the 40% there is no pulse. And again this same thing is repeated here. Okay, so we need to find the average voltage across A and B. First of all, let's see what will happen when there is gate pulse. We are providing gate pulse to the ideal MOSFET. What will happen? Whenever you will provide a gate pulse like this, the MOSFET will be on, right? So an ideal MOSFET will be, there will be no drop across this MOSFET. So it will be this point and this point, these 2 points will be short. So the equivalent circuit will be like this. Because the MOSFET is shorts these 2 points, that's why these resistors will get bypassed, right? And the current path will be like this. The diode is connected in series with this voltage source. The diode is always forward biased, right? Because the anode terminal is connected to the positive terminal of the DC source. That's why the diode is always forward biased. So the equivalent circuit will be like this. Okay. And there will be no current through these resistors. Is it fine? Everybody understood why the equivalent circuit becomes like this? Because the MOSFET is on now. When we are providing the gate pulse, that's why it becomes a short, like it bypasses these resistances. Okay. So during this period, as these 2 points are short, A and B, these two terminals are short now, so there is no voltage. So during this time duration, VAB is 0. That's what I have written here. When gate pulse is not provided, current flows through the load resistance. Okay. So so when gate pulse is provided, MOSFET is on. So VAB is 0. And when gate pulse is not provided, that is during this duration, when gate pulse is 0, that time the MOSFET is off. So then the current will flow through these resistors that we will see, the equivalent circuit we will see. So for first instant, when gate pulse is there, this is the equivalent circuit. And when we don't have gate pulse, this is the equivalent circuit. So there is no gate pulse, so the MOSFET is off. So there is the path here is broken, right? So now the current will flow through these resistors. Okay. And if you calculate the equivalent resistance, what is the equivalent resistance? There is this 1 kilo ohm, and here there are two resistors, each having a value of 2 kilo ohm. So this equivalent resistance becomes, what will be the equivalent resistance of this portion? Can anybody tell what will be the equivalent resistance? This is very easy, right? So here the equivalent resistance is 1 kilo ohm, right? Because two resistors are in parallel, they are connected in parallel, and each of them has a value of 2 kilo ohm. So the equivalent resistance becomes 1 kilo ohm, right? So there is 1 kilo ohm resistance here and another 1 kilo ohm resistance here. So the total resistance becomes 2 kilo ohm. Okay. So the current flowing through the circuit will be 20 divided by 2 kilo ohm. Okay. And the voltage across then we a like voltage across these two terminals will be 10 volt because this is 20 volt. There is this 1 kilo ohm, another 1 kilo ohm. So the voltage drop across these two resistors will be equal because their resistance values are equal. So 10 volt will be dropped across this resistance and 10 volt will be dropped across these two terminals. So that's what I have drawn here. So when the gate pulse is 0, some voltage appears across A and B, and that voltage is 10 volt. But this is an instantaneous voltage, mind it. This is not an average value, right? They have asked for the average value of VAB. So this is the instantaneous value, 10 volt. What will be the average? Average will be the for that we need to integrate it over the total time period. So it is very straightforward. For 40% duration, can you please mute yourself? So for 40% duration, you have this 10 volt. So what will be the average value? Simply 0.4 times 10 volt, that is 4 volt. Okay, that will be the average voltage across these terminals, A and B terminals. Is it fine? Did you understand how I calculated the average value? If you don't understand, please ask, okay? Because in your assignments, you will get similar kinds of questions. So, if you don't understand any point, just ask, okay? Okay, so I think everybody is clear. I shall go to the next problem. In the next problem, what they have asked, they have asked that find the total conduction loss in the diode in Q question 1 if forward voltage drop of the diode is 0.6 volt. So earlier in the question, they mentioned that you assume an ideal diode. For an ideal diode, there is no voltage drop and there is no loss in the diode, right? But here they have told that the forward voltage drop of the diode is 0.6 volt. So this diode is no longer an ideal diode. There is some drop across this diode in the forward bias direction, in the forward bias condition, and that voltage drop is 0.6 volt, right? So now we need to calculate the conduction loss. For calculating the conduction loss, what we need? We need the current through the diode, right? That's how we will calculate the conduction loss. So if you see, when the gate pulse is provided, the MOSFET is on. That time, what is the current? Current through the diode ID is 20 minus 0.6 because they have told the drop is 0.6. That's why 20 minus 0.6 divided by 1 kilo ohm, this resistance. So this current comes out to be 19.4 milliampere. 1K means this is 1000 ohm. 1 kilo ohm means this is 1000 ohm. So I have expressed it in milliampere. You can also write it in ampere, whatever is whatever is okay with you. And when the MOSFET is off, that time it is not here, the equivalent circuit becomes this. So that time what is the current? The equivalent resistance is 1 kilo ohm. This is also 1 kilo ohm. So the total resistance is 2 kilo ohm. So here we have again subtracted zero point 0.6 from 20 divided by the total resistance, which is 2 kilo ohm. This current comes out to be 9.7 milliampere. Okay. So for 60% of the time period, the current is 19.4 milliampere, and for 40% of the time period, the current is 9.7 milliampere. From this waveform, you will have to calculate what is the average current through the diode. Okay. So if you just calculate the average current here, what you will get? The average current will be 19.4 times T plus 9.7 times 1 minus D, where D is the duty. Duty means duty cycle is basically when the MOSFET is on. The on duration is called the duty cycle or duty ratio. So the duty ratio here is 0.6 because till this time we are providing the gate pulse, right? And from 0.6 ts to ts, the gate pulse was 0. That's why here the duty is zero point 0.6. So till this duration, the current was 19.4. That's why into D. And in this duration, it is 9.7. So 1 minus D. So ID average comes out to be 15.52 milliampere. And here they have not provided any diode resistance. So actually the conduction loss is ID average into VD average into VD plus ID RMS square times RD, right? That we have already seen. But here the resistance is not provided. That's why simply we will do the conduction loss is ID and ID multiplied by VD. And that comes out to be 9.312 milliwatt. Okay. Is it clear till this point? Okay, so let's go to the next problem. So it is also part of the first question. What is the power delivered by the voltage source in question 1 considering diode drop? So what is the power provided by this voltage source? And we will have to consider the diode drop also. So simply the power delivered by a voltage source is the voltage multiplied by the average current coming out of this voltage source, right? So the average current, so here the diode is basically in series with this source, right? So whatever current is coming out from this source that flows through the diode. That's why the
और
average current.
डीसी से स्टॉप ऑनलाइन ट्रेन सेट 605 आईवीएल 2 से आईवीएल 3 की ओर मूव कर रही है 605 ओके
Can you please mute yourself? Yeah, so what I was saying is that whatever current comes out from whatever DC current comes out from this source, that current only flows through the diode because they are in series. So we have already calculated the diode average current. So what we'll have to do is simply we will have to multiply the average current and the voltage value, which is 20 volt. So this will be the power that is delivered from the source, 0.31 watt. Okay. Let's go to the next problem. Here what they are asking, that consider the circuit in the figure below which uses IRF 260M PBF MOSFET for switching. So they have mentioned a particular part number. So this MOSFET data we will have to use. Okay. Calculate the switching loss associated with the MOSFET for the given gate pulse. The gate pulse pattern is provided. Here the switching frequency is given 10 kilohertz. Consult the datasheet of IRF 260M. So this part you will have to search this part number and use appropriate parameters wherever necessary. So they have asked for the switching loss. To calculate the switching loss, what we need? We need the rise time, the fall time, right? Because when the switch is transitioning from off state to on state, during that time the current will rise, and that time is called the rise time. And when during when it is transitioning from off to on, from on to off, that time the current will fall, and that duration is fall time that we already saw in the dynamic characteristics. We need these two parameters for calculating the switching loss, right? And this is the gate pulse, and the frequency is 10 kilohertz. Okay. So here I have collected the data from the data sheet of this particular MOSFET. You can check it by yourself. So here the TD on, the turn on delay time is provided 17 nanosecond. The rise time is provided 60 nanosecond. The turn off delay time is provided 55 nanosecond, and the fall time is provided 48 nanosecond. So we need these two times, rise time and fall time, for calculating the switching loss. Okay. And in the data sheet, you will see that all this data is given for a particular VDD, particular drain voltage of 100 volt, ID of 28 ampere, RG. RG means this is the gate resistance. Okay. This is the gate resistance, and VGS is 10 volt. So at this particular operating points, we have the rise time and fall time are provided. But you will have to remember, as these operating points are changed, these times will vary. They are functions of these parameters. So as long as they are constant, we can take the values. But if one of these parameters are different, then this rise time and fall time, they will also be different. Okay. But anyway, for now, we can take these values right away. So this is the dynamic characteristics that we already saw. So this is the delay time. So we will not take into account this loss because here the current is too small. So we don't have to worry about this time duration. But here there will be some loss because here the voltage is falling from this VDS to zero, almost zero, a very small value, and current is rising from zero to this value. Okay, so both voltage and current both are present, so some loss will be there. This is the turn on loss, and this is the rise time. And similarly here we have the fall time where the current again falls back to zero and the voltage rises here. Okay. So similar exercise we did for BJT also, BJT and diode, where we calculated the turn on and turn off losses. Okay. And for MOSFET also, we will do it in the same manner. So the rise time is 60 nanosecond, fall time is 48 nanosecond. And P on, the formula for turn on loss is VDD ID times rise time by 60s. And for off loss, the formula is VDD ID times TF by 60s. So the derivation of these formulas, I already told the method for BJT. For MOSFET also, you can find out in similar manner. So what you need to do is you just need to write the equation of VDS with respect to time during this interval, and also you can have the equation of current with respect to time during this interval. What you need to do is you need to integrate it with over the time period, the total time period. Okay, and from there you will get this formula. Okay, I have shown it in the last video. Okay, in the last week's video, and you can ask if you don't understand. I will again show. So this is the turn on loss, this is the turn off loss. And switching loss is the summation of turn on loss and turn off loss. Okay, so the summation of these two. Now what we need to do is we need to find out the value of VDD and the value of ID, because we already have TR and TF values, and we also know the frequency is 10 kilohertz. So our TS will be 1 by 10,000. Okay, that will be our TS. That is the time period of the time period, right? So yeah, so here if you just look at this circuit, when we are providing the gate pulse, let me just show you the gate pulse here also, then it will be. This is the gate pulse. So here the duty is 0.4, right? Because for 40% duration we are providing the pulse, and rest of the portion, the 60% interval, there is no pulse. So when we are providing the pulse, obviously the MOSFET turns on, and there is some channel resistance, right? So the channel resistance you will also get from the device data sheet, and the channel resistance, that channel resistance is there. So you can just, when the MOSFET is on, you can assume the MOSFET as a simply a resistance. Okay, so here instead of the MOSFET, you can just assume a resistance, and that resistance value will be the RDS on of the device that we will get in the data sheet. So here there will be two resistors which are in parallel, and here there is another resistor. Okay. So you will have to calculate the equivalent resistance, and then you can calculate what will be the current through this MOSFET. Okay. So yeah. So I will just I will draw it a bit so that you can understand properly. So when the we are providing this pulse, the equivalent circuit will be something like this. Okay. So here there is this 20-volt source. There is this resistance. And here instead of the MOSFET, we can draw a resistance. Okay. Because during the in the on time, the MOSFET acts as a simple resistance. We can model it just as a resistance. Okay. So this is 10 ohm. This is RL. Okay. This is RL. And this resistance is given 10 ohm. And this resistance, which is basically the MOSFET model for now, that is RDS on. Okay. RDS on this resistance. And from the data sheet, if you just see the data sheet here, the RDS on value is here. RDS on is RDS. RDS value here is 0. Sorry. 0.0 4 ohm. Okay, that is the RDS on of the device. It is provided in the data sheet. Okay, I have seen it from data sheet. So if you just solve this circuit, so here there is a 10 ohm resistance, here it is 0.04 ohm, here it is 10 ohm. You will get the equivalent circuit. And if you just divide the equivalent resistance, like 20 divided by the resistance, you will get the current this path, through this path. And this current is getting divided between this MOSFET and this another resistance. So most of the current will obviously flow through the MOSFET because RDS on is much less than this resistance. So the current value is 1.984 ampere. Okay, you can solve this when the MOSFET is on, and VDD value is the voltage value when the MOSFET is in off condition. That time the MOSFET blocks some voltage, and that voltage is 10 volt. Okay, because that time this path is open, because the MOSFET is off, this path is open, so the current will come from this node, and it will flow through this resistance. So that time the equivalent resistance will be 20 ohm, right? 10 plus 10, because there is no path here, it is off, and the voltage drop across this resistance will be 10 volt because they are equal resistances. So this 20 volt will get dropped across this resistance and this resistance equally. This voltage will be 10 volt. Okay, 10 volt. And that's why I have written VDD is 10 volt. But remember, this is during off condition. Okay, when the MOSFET is blocking some voltage. And this current is when the MOSFET is carrying current. Right. So we have the ID value, we have the VDD value. From this formula, we can calculate P on and P off values, and we can simply add them to get the P switching, which is 3.57 milliwatt. Right. This will be our switching loss. Is it fine? You understood, right, how I calculated the switching loss? Okay. So let's go to the next problem. Here they are asking, calculate the total conduction loss in the MOSFET in question 4. So the same problem, uh, what they are asking, that what will be the conduction loss in this MOSFET. Okay. So conduction loss is very straightforward. You just need to know the RMS current that is flowing through the MOSFET and the RDS on. So if you know these two quantities, the conduction loss will be simply ID RMS square times RDS on. Okay. Yeah. So here, what is the ID RMS? Here I have drawn the current waveform, right? So here there is pulse, so the MOSFET carries some current, and that current we already calculated. The current value is 1.984 ampere. And after that, the pulse is withdrawn, so there is no current. Again, there is pulse, so again there will be current. So this is one time period. From 0 to TS, this is one time period. And after that, it gets repeated, okay, in each cycle. So if you, this is a square wave, right? For calculating the RMS of a square, like square wave, not a square wave, like this part is a square wave and then some part is zero. So if you just calculate the RMS of this waveform, it will come out to be ID times root D, where D is the duty ratio, right? Here the duty ratio is 0.4. And ID we already calculated 1.984 ampere. So ID RMS becomes 1.254 ampere. So, and we already saw the RDS on was 0.04 ampere. So the conduction loss is ID RMS squared RDS on, which is 62.9 milliwatt. Okay. This is the conduction loss that is happening in the MOSFET. And earlier we also calculated the switching loss of the MOSFET. So if you just add all these losses, you can get the total loss that is occurring in the MOSFET. Okay. Yeah. So let's go to the next problem. So this is a multiple choice question. MOSFET is which type of device? So we already discussed it is a voltage controlled current device. Okay. This is a voltage control device because controlling the gate to source voltage, we can control the turn on and turn off of the device. Okay. So that's why it is a voltage controlled current device. Next we have which of the following device has controlled turn on and uncontrolled turn off characteristics? So the options are SCR, diode, IGBT, MOSFET and triac. So we studied about SCR, diode, IGBT and MOSFET, but we don't know about triac. Okay, what is a triac? So
Excuse
while
me.
yes,
Excuse me.
yes.
क्वेश्चन नंबर 5 रिपीट कर सकती हैं क्या आप?
Sorry, question number
5
okay, question number
मैं
5. Okay.
मैं थोड़ा डिले हो गया मैम.
Okay, okay. So this question only, right? The conduction loss part.
यस मैम.
Okay, the switching loss part you understood?
यस मैम.
Okay. So while calculating the conduction loss in a device, we need two parameters. First one is the RMS current. The second one is the device resistance. Okay, during on condition. So for MOSFET, there is a parameter called RDS on. RDS on is what? When the MOSFET is on, there is a resistance of the channel. I already told you that a channel is formed when the MOSFET starts conducting. So there is some resistance of the channel which is a very low value. So and that resistance value is provided in the data sheet. Okay. And earlier we saw the resistance value was 0.04 ampere. You can check in the here the part number is provided. This is the part number. So if you just search in the web this part number, you will get the data sheet and you can check what is the RDS on. Okay, you will get the value. That value is 0.04 ohm. We already have RDS on. Now we need to calculate only the RMS current. For calculating the RMS current, we need first see what is the current waveform. Okay. So when we provide pulse to this to the MOSFET will conduct, and this current value we already calculated while doing the switching loss calculation. That current was 1.98.
ये ड्यूटी साइकिल है टर्न ऑन कंडीशन का है 0.4 ना.
Yes, yes. During this time we are providing a positive gate to source voltage. That's why
यस.
the MOSFET is on. Okay. And when the MOSFET is on, it will carry some current, right? So that current is 1.984 ampere that we calculated in the last question. While calculating the switching loss of the MOSFET, we saw the current was 1.984 ampere, but this is the instantaneous current, right? And when we are not providing any gate pulse, then there is no current through the MOSFET. This is the MOSFET current.
ओके ओके
Okay.
अंडरस्टैंड.
So there is no current. This is zero. So so now what you need to do is you need to calculate the RMS current of this device. So for some duration there is this current and after that there is zero current. So what will be the RMS current expression? It will be simply ID times root D. you can calculate the RMS current expression like conventionally how we do, like integration of this IT square dt over this time period, root and square root. Okay, how we usually do the RMS expression of any waveform. If you do that, you will get this kind of expression, ID times root D, where D is the duty ratio. Duty ratio here is zero point 0.4, right? Because 40% of the duration we are providing pulse, that's why the duty ratio is zero point 0.4. So the current comes out to be 1.254 ampere, and then you can simply find the conduction loss by doing this calculation, ID RMS square times RDS on. Okay, is it clear?
Yes, ma'am.
Okay, okay. Yeah, so we already saw this question. Next, we were discussing about this question. Which of the following device has controlled turn on and uncontrolled turn off characteristics? So we know about SCR, we talked about SCR, we talked about diode, we also talked about IGBT and MOSFET, but we don't know what is a triac. So basically, triac is a device which belongs to the SCR family. So there are various different devices that belongs to the SCR family. Triac is one of them. Okay. There is diac also, but these devices are not very common nowadays. They are not used. But earlier, yeah, like sometime back, they they were in use in industries and for different applications. Nowadays, they are not used really. But anyway, we will see. So here we have diode, we have SCR, and this is the symbol of a triac. So you can see there is this diode kind of symbol, but there is a back-to-back, there are two diodes back-to-back. One is like this, and one is like this. Okay. And there is one control terminal also. So for diode, we know for diode, the things are very simple. There are two terminals. It is obviously uncontrolled device. So diode is not the correct option, obviously. Its turn on and turn off depends on the biasing voltage, and the biasing voltage is depends on the circuit condition. And so diode is not the correct option. For SCR, we know that the turn on we can control by providing the gate current, right? We saw that we can control the turn on, but the turn off is uncontrolled. Okay. For triac, again the turn on is controlled because we have this third control terminal, and turn off is uncontrolled, but it has bidirectional current because there is this back-to-back condition, back-to-back structure. That's why it can carry current in this direction as well as this direction. Okay. Our question was, which of the following device has control turn on and uncontrolled turn off characteristics? Okay. So although triac has uncontrolled turn off, but it has been grouped with MOSFET. So this option we can't take. The only correct option is SCR because for SCR the turn off is uncontrolled. Okay. So the correct option is SCR. And MOSFET IGBT, so we already talked about. For MOSFET and IGBT, both of them, both turn on and turn off, they are controlled. Okay. We can control both the turn on transition, also turn off transition. So these two options are not valid. Only the correct option is SCR. Okay. SCR is, that's why it is called semi-controlled device, because only turn on is controllable, turn off is not controllable. Yeah, so another question we have, one of the differences between diode and triac is. So there are four options. Diode has control turn on and triac has control turn on. So this is definitely wrong because diode is not controlled device. Diode doesn't have control turn on. This is wrong. Second option is diode has control turn off and triac has control turn on. So this is again wrong because again we can't control turn on and turn off of a diode. So this is again wrong. Third option is diode needs gate pulse to turn on and triac doesn't need. Again, this is wrong. Diode, there is no gate, like there is no gate terminal only for diode. Diode has only two terminals. So this is again wrong. Diode has unidirectional current flow and triac has bidirectional current flow. So obviously this is the correct one because we saw that for diode the current can only go from anode to cathode, not in the reverse direction. But for triac, current can go in either directions, from this side to this side as well as from this side to this side, right? Because of its structure like this. It is kind of the combination of two diodes which are connected back to back, and also it has a third terminal which is the control terminal. So the fourth option is the correct one. That diode has unidirectional current flow and triac has bidirectional current flow. Okay. Next we have another question. Which out of the following has a transconductance curve in the second quadrant? So this we have not discussed. So as I was telling that there are different kinds of MOSFET. Okay, there is enhancement type MOSFET and there is depletion type MOSFET. Right. Here we have all these options: BJT, MOSFET, JFET, and IGBT. Okay. So for BJT, transconductance curve means that uh, just a minute. So we saw what is a transconductance curve. So transconductance curve means here there will be VG, V gate to source. Okay. And here there will be I drain current. Today only we saw for MOSFET, right? The transconductance curve. So for which of these devices this curve is in the second quadrant? Second quadrant means in this region, in this quadrant. So whichever devices we have studied so far, BJT, MOSFET, IGBT, all of them has curves like the transconductance curve in this portion. For IGBT or BJT, the transconductance curve will be here, the voltage will be V base to emitter because base is the control terminal. Okay. VB, and here it will be I collector. Okay. So for them also none of them has the transconductance curve in the second quadrant. Both of them. So for MOSFET also the curve is here. So the curve starts like this. Here this voltage is the threshold voltage VTH. VTH. Okay. And for BJT also the curve is something like this. So none of them has the characteristic in the second quadrant. Only one is remaining, that is the JFET, and we have not studied this. So let's see what is the characteristic for JFET. Okay. Junction field effect transistor. Sorry. So let's see. So I have shown here three characteristics. Okay. You can also refer to the lecture. There it is explained what are the different types of FETs, like field effect transistors. So first one is the convention, like first one is the one that we already studied, right? We saw in the data sheet. The curve is something like this. This is the V threshold, and after V threshold is crossed, the current starts rising, and the relationship is something like this with ID and VGS that we already saw. And this is the enhancement type MOSFET. Why this is called a enhancement type MOSFET? Because whenever we provide a positive gate to source voltage, that time a channel is formed and carrier concentration increases, right? There is a channel formed, and the channel is formed by because the electrons are attracted towards the positive terminal of the capacitance, right? We saw this. Uh, Here we saw this, right? That when we were discussing the MOSFET here, yeah. So, if you see here, whenever we provide some positive gate to source voltage, the electrons are attracted towards this terminal, right? Because if you assume this as a capacitor, so this will be the positive terminal of a capacitor and negative charges will get attracted towards this. So here the carrier concentration increases as we give positive gate to source voltage. That's why it is called enhancement type MOSFET. The depletion type MOSFET is opposite to that. So if you see these characteristics here if you see this characteristic starts here when the gate to source voltage is negative, right? And from here only the current starts rising, and after in the positive direction also it rises. So this is a depletion enhancement type MOSFET because the characteristic has some of its part in the second quadrant and some of its part is in the first quadrant, right? So this is kind of a hybrid MOSFET. It has a depletion characteristic as well as enhancement characteristic. And this is the relationship. And the third one is the depletion only JFET, where this characteristic is only present in the second quadrant. So in this, there is this negative VGS from where the ID current starts, and when VGS voltage is zero, then there is some ID current, right? But if you see for this MOSFET, when VGS voltage is zero, there is no current. After the threshold voltage, it starts rising, but here, when VGS is zero, that time there is some current. Okay. And this is called the depletion type MOSFET because as the gate to source voltage increases, right, so from negative it starts and it goes towards zero voltage. So the carrier concentration actually reduces. Okay. So that's why it is called depletion only JFET. So our correct answer would be JFET because it only this device has a transconductance curve in the second quadrant. Right? So yeah. And this is the question. Which of the following is a feature of MOSFET? Right? There are four options. So you guys tell which will be the correct options here. Among these four options, which are the correct options?
Ma'am, option C.
Yeah, because this is the bidirectional current device, right? So option C is definitely correct. And is there any other correct option? What about the voltage blocking capability? MOSFET blocks voltage in only in a single direction, or it can block voltage in of both the polarities.
Single polarity.
Unipolar, right? So option B is also correct. MOSFET has unipolar voltage blocking capability. right? So these two options are correct. So I think we have covered all the questions. So does anybody have any question regarding the numerical problems, or regarding the summary part that we discussed today?
मैम ये क्लास डेली चलती है क्या?
No, it's not a daily class. This is a weekly class. Each Monday from 6 to 8.
ओके मैम, मेरे कुछ असाइनमेंट छूट गए पीछे के, वो फर्स्ट एंड सेकंड, तो मैं इसको कैसे कवर करूँ?
So if you want some content, then you can refer to the lecture video of Umanand sir. And I also have uploaded the last 2 weeks video in YouTube. Okay. So I think you have access to the videos. You can refer to them. I have also uploaded the presentations in the drives folder. All these links, you will have access to all these contents. And if you want to know about the if your deadline is over, then I think you will have to contact to NPTEL. Okay, you will have to mail, or you will have to contact them and ask what to do if you have crossed the deadline.
Okay.
Because we are only here for conducting the tutorial sessions. Okay, regarding the assignment submission and timely submission, or you have skipped the deadline, then you will have to contact you have registered for this course, right? E37.
Yes, ma'am.
So you can mail them and ask what to do if you have missed any assignment deadline. And if you want to check these videos, they are available. They are available in YouTube, and you can the links are provided, I think, so you can check them anytime. And these presentations also I upload each week. You can refer to them as well. Whatever assignments you get, they should be very similar to these questions that we solve. Okay. So they will be in line with these problems. They will not be exactly same, of course, but uh, very similar to these problems.
Okay, thank you, ma'am.
Okay, thank you. If nobody has any question, then I think we can end today's session. Thank you for joining. Okay, thank you.
Thank you, ma'am.
Thank you.